Guys, my name is Ernest and I'd like to welcome us to Ernest Sciences and Mathematics TV channel. Now in this particular discussion I'm going to show how we can obtain the eigenvalues, and in our last discussion I talked about the concept of eigenvalues and functions, which of course I said culminate from the normalization condition of this specific general description of our wave function given in terms of the the sine over n pi x over L. And of course, I've said that we can find the unknown value for this specific constant over A by creating a normalization condition of having this particular probability of the particle given as 1. And of course, I said that this is equivalent to 2L the sine over n pi x over L, where L is the distance between these two specific regions, considering a one-dimension box given as such. So in this specific part, we're going to find a way of describing this specific aspect of the eigen values, which are described in terms of n squared, h squared over 8 ml squared given as such. And of course, I've said that in representing this specific aspect of the eigen values, we can have eigen functions represented, particularly in terms of that representation of using the wave function given as such. So in this case, I'm going to just have a small recap of what we have discussed, and that is going to create for us a basis of describing these two specific aspects of the representation for this one-dimension box for the wave function and the absolute value of the square of that wave function given as such. And in this case, of course, I've given the graphical representations for the values of n equivalent to 1, n equivalent to 2, n equivalent to 3, given in that specific order. And therefore, I'm going to look at the general equation, which, of course, I've given in terms of this is a wave function, the root of so this is a normalized wave function for the representation of a particle in a one-dimension box, which are given in terms of this specific representation. And therefore, from this, to find the eigenvalues, we are going to have this value of k, which are given the square of k from the Schrödinger's wave equation, given as a product over 2me divided by this particular form over h. And I've said that this h basically represents h over 2 pi, and therefore the square of this represents the h squared over 4 pi squared given as such. And I'm going to use this reduced form in that specific order. Now, secondly, we said that we can find the value of k by n pi over L, and this is from the concept of the aspect of the value from the wave equation, giving us the sine over kl given in that specific order. And we had said that the value of a is not equivalent to 0. Therefore, this second aspect of the function is going to represent 0. And from the description of trigonometric graphs, we said that for the value of this particular aspect of the sine over kl equivalent to 0, this is equivalent to k l equals to the integer values of pi, and therefore we're going to have this one giving us the value of pi given as k is equivalent to n over n pi over l given as such. So we can represent this specific aspect of the value of pi, the square of pi, given this first statement which I have given in terms of an equation, and also have an equivalent of the square of pi from this second aspect, having as the square over pi squared over l squared given as such. So the equation for this one and the equation for this one for the left and right side are going to be equivalent. Therefore, we're going to have 2me representing what we refer to as the square of n pi squared over l squared given as such. So this is an equation of this one and this one given in terms of this format. So this generally is going to give us the value of e representing the square of nh squared all over 8ml squared given as such. And this was a general representation of finding the eigen values of a particular function. Now in this case, this is going to have an implication where we're going to consider the value of n in this case from these two specific illustrations for the first for a and b. And therefore I'm going to just have a detailed look at this individual cases for the values for perhaps values of n equivalent or n ranging from 0 going on to perhaps 1, 2, 3. And in our first case, we had said that basically we're going to consider the values of n ranging from the first one going on as that. And as we said, that n is going to represent the quantum number, which is basically a description of the various energies which can be illustrated using that one-dimension box of potential 0 given as such. So the first case I'm going to consider where the value of n is equivalent to 0. And in that case, from the general representation of the Eigen values for n equivalent to 0, we are going to have this particular value for the numerator. Whenever it is equivalent to 0, then therefore we're going to have this value over the energy given as 0, and therefore our Eigen value is going to be equivalent to 0, and the Eigen function in this particular case therefore is going to be equivalent to 0 as well. And we can be able to describe this, or we can describe this particular state for the value of n equivalent to 0 as the motion of an electron that is sustained or showing no activity in that particular case. And if you consider the value of n is equivalent to 1, we're going to have this one given in terms of the Eigen value of E1 given in that specific order, whereby we're going to have a substitution of 1 here, giving us the square of Planck's constant ml squared given as that. And this is going to be the Eigen value of this particular case. And the Eigen function for 1 is going to be a value whereby we're going to have the root over 2 over L. And of course, in that specific case, we can represent this specific value using this case. Now, if you look at the specific illustration for the A and B, A represents the wave function given as such for n value of n, and B is going to represent the square of that absolute value of that wave function, and therefore that's going to indicate the probability of finding an electron. So in this case, for n is equivalent to 1, that is going to imply a situation whereby the function is going to be have a maximum displacement of the electron at exactly the middle part of this specific illustration. So I'm going to have to represent this one. So at this specific point, we are going to have a maximum displacement, which is going to represent the maximum value for that probability of finding an electron for both the wave function and the square of the wave function given as such. So next I'm going to consider a case whereby we're going to have, so this is E equivalent to 0, or n equivalent to 0. Now for n equivalent to 2, I'm going to have this one represented in terms of a 4h squared over 8ml squared. And this is a substitution for this value of n, and therefore the Eigen value for the case in this particular case is going to be given for the square of the wave function and the wave function given in this specific wave. And therefore we're going to see that at this specific point for n equivalent to 2, we're going to have the Eigen value represented in that specific format. And this can be given in terms of 4E1. So there are going to be a multiples of this specific function for E1 as I've mentioned. Therefore, we can represent the Eigen function of this specific case given in terms of, so we're going to have the root over 2 over L, and then we're going to have the sine over 2 pi x over L given in that specific order. So that one is going to go on, and then we're going to see that for the description of this specific case for E is equivalent to 2, we're going to have the maximum displacement of the electron at the quarter distance from either sides of the box, whereby we're going to see that at this specific point, this is the middle point, and of course the description for this specific maximum displacement is going to occur at the quarter position of this specific function. Now for the positive of this square of the function being indicated at these two specific points. From the sides of the box as I've mentioned. So lastly, we're going to consider the case of the value of n is equivalent to 3. And in this case, we can describe the Eigen value for the value of n is equivalent to 3 using this specific Eigen function, where we're going to have this one as the wave function equivalent to 3 is given as the root of 2 over L, and then the sine over 3 pi x over L given as such, and the value in this specific case is given in terms of 9e1. So basically we're going to consider the specific function of this one as we rise up the energy from 2 to 3 given in these specific multiples. And of course they are going to give us the probability of finding these electrons in these various parts of the the wave. And the maximum displacement, of course, is going to be exactly in the middle and a sixth the distance from this specific point of the two walls. So we're going to have this one indicated as that, and then these are divisions. So therefore, this specific point and this one, and for this one, we're going to have it at this specific point. And this basically considering these various nodes, we're going to see that this is going to be 1, 2, 3, 4, 5, 6. So it's going to be a sixth position from these two sides of the walls, which are indicating the maximum displacement for that specific aspect of an electron. So basically from the graphical form or the one box in one dimension, we can represent the various aspects of eigenvalues and eigenfunctions using that specific aspect. So catch us in our next video and check our description boxes for various links of other videos which are going to assist us comprehend this specific aspect. So that is it for now, guys. Bye, God bless you. Catch us in our next video.